Okay, we're gonna get started, everyone. Welcome to our last day of Two Horses. I hope you all had fun at the barbecue last night. And starting us off this morning is going to be Nicholas Borsato talking to us about KELT-9b.
Cool. Hi, everyone. So I'm Nick. I'm a CoachUtel PhD student, which is a fancy way of saying I did my PhD at 2 universities. So I'm currently residing at Macquarie University in Australia, but I also spent 3 years studying with Jens at Lund University. So I'm in my final year of my PhD, and I could pretty much summarize what I've done for the last 4 years in one sentence: high-resolution transit observations of KELT-9b. So for 4 years, I'm not one to flog a dead horse, but somehow I seem to keep coming back to this planet and finding more and more data sets to analyze. So at the moment, I now have 13 transit observations of KELT-9b over 6 different spectrographs, spanning a wavelength range down to almost the near ultraviolet and up to the near infrared. And the main science case for this project is that really blue wavelengths, or purple wavelengths actually, start to probe metals in the atmosphere of KELT-9b that we haven't seen before. So there are a lot of lines that we just haven't been able to probe with other spectrographs that my high-res observation on the Keck telescope has. So before I get into my results and my method, I want to sort of briefly cover the cross-correlation method that we've been seeing a lot this week. So often you'll see this cross-correlation trace, which tracks the radial velocity of the planet. Then we transform that into a KP-V-Sys diagram, which allows us to show that a detection has occurred at the planetary velocity, the KP, and the systemic velocity, V-Sys. And then you take your favorite row of that KP-V-Sys diagram, and then you say this is an average line depth of the planet. There are some inherent problems that we've sort of begun to discuss in this conference by doing things this way, especially when looking at the KP-V-Sys diagram. Namely, there's two things. One, that blob is quite degenerate. So where exactly is the planet in that blob? You might try and look for a maximum, but it's a bit hard to draw inference from those types of results. And two, KP-V-Sys diagrams are very collinear in their data set. And if you ever do any kind of statistics with that, collinearity can destroy any statistical significance that you have, or really muddle kind of results that you have as well, which makes things difficult. So what my group at Lund have started to do is sort of reframe the cross-correlation problem, and we use an MC approach. So the idea is that, well, we know the rough analytical approximation for the transit of an exoplanet, so why not parameterize that by making using a Gaussian function and then using the centroid to sort of follow the transit curve as a function of radial velocity and orbital phase. And when you do that, you're able to extract parameters like V-Sys and the KP, but you can actually also, using an MC-MC framework, you're able to obtain uncertainties as well from that in a way that is a little less ambiguous than using a KP-V-Sys map. So looking at this result, I'm just going to explain the top. So in the top left-hand corner, you see the CCF result. And a lot of you are probably squinting your eyes and like, that doesn't look like a very strong KP-V-Sys trace, well, sorry, a CCF trace. And I need to remind you that you're looking at both 10-meter telescope data and 2-meter telescope data simultaneously. And so the contrast in signal to noise is just washing out the signal. But if you weigh each night correctly, you can fit a very strong cross-correlation trace to that, and then you can transform the V-Sys values independently of each other to obtain basically a V-Sys detection, both with the data and with the model itself. And so you can see that our method actually produces a pretty good agreement between the two things. Finally, when you have this MC-MC framework, you can start to have a bit of fun with the parameterization. So what we actually did was we added a gradient to the amplitude. So to basically measure, does the transit signal get weaker or stronger at the beginning or the end of transit? So if you have a negative amplitude gradient, that means that you have a stronger signal at the beginning of the transit, and a positive gradient means you have a stronger signal at the end of the transit. So now to sort of the fun part. Using this method and the 13 nights of observations over 6 spectrographs, I've managed to detect 40 species in KELT-9b's atmosphere. Pretty much we're starting to uncover different species in the periodic table, and some structures are beginning to form. Basically, everybody's favorite metals are pretty well found, but we're also seeing that lanthanides are very detectable, and also the 3 columns from calcium to titanium also seem to be quite detectable. So the high scorers in this result are erbium, hafnium, and bismuth. I almost missed bismuth because it's in the bottom corner of the periodic table, and I was like, I better check everything, and then it popped out. So yeah, so kind of crazy. So then the question that you want to ask yourself is, what do we do from here, right? Everybody says that you have cross-correlation detections. The next step is to start doing abundances. And I agree, but I also think there is some other science that I can do now that I have 40 detections. So the answer I came up with was, let's do some statistics on these detections. So what you're seeing here are scatter plots of the VSIS on the left versus the amplitude gradient that I talked about, and the KP on the right versus the amplitude gradient. And what you can see is they don't all agree. And there seems to also be some sort of structure in these detections as well. So when I had all this, I was sort of like scratching my head, and I was like, well, I need to sort of try to explain why this is the case. And so that's basically what I endeavored to do. So I went and grabbed the VSIS and the KP values, and I measured their distributions. So what you're seeing here are histograms of the VSIS and KP values with incorporating their uncertainties. So basically I did a Monte Carlo simulation to robustly create these distributions. And what you can see are some interesting effects. So for the VSIS, we seem to have a central peak, which is very close to the systemic velocity of KELT-9b, and then 2 side lobes that are roughly symmetrical to each other. And then for KP, we have the measured KP, or the average, the peak KP value is offset from the actual orbital velocity of the planet if you just assume a circular velocity and you calculate it for yourself. So what's going on here, and why is it that we have these weird detection characteristics? Well, if I attack KP first, because it's a little bit easier to explain, I first want to talk about why we have this offset in this peak. So if Usted did a really good talk yesterday talking about the geometry of the planets of ultra-hot Jupiters. So an ultra-hot Jupiter has an inflated day side and a cold night side. And what that implies is that you actually have an asymmetric geometry which is observable when you observe a transit. So when the planet moves towards you in the ingress phase, it actually rotates away from you. And then the opposite occurs during the egress phase as well. And so what happens is this actually will create a lower offset in your KP value, because basically you're quote unquote subtracting some sort of velocity profile from the rotation that you're getting from your gradient. So this is a top-down view of KELT-9b, assuming a differential rotation profile. And if I extrapolate this out, you can see that if I assume that we have symmetrical limb contributions with no hotspot, our VSIS stays consistent, but with our toy model, if we increase the scale height of the hotspot, the VSIS starts to drop down further and further as well, suggesting that there's some sort of relationship with the scale height of the inflated atmosphere and the KP detections that you see. So I'll go back to, there's also another part of the KP distribution. It actually has a skewed tail to the right, and I'll explain that in a second, but I need to jump now to VSIS to do that. So when I look at the VSIS, the first thing I thought is, oh, maybe it's rotation in the planet. So I fit a rotation kernel, and I got something that was kind of unphysical. So I was like, okay, well, I don't know what to do then. Then I sort of woke up one night at 1 o'clock in the morning, and I had an idea. What if I just take an average of the KPs of the 2 side lobes and the central lobe itself? And what happens is, if I take an average of the KPs with the blue and red regions, I get around 260 kilometers per second, which is actually higher than KELT-9b's orbital velocity, while in the center of that distribution, we see that characteristic drop that I just explained. So then I'm like, okay, well, what's going on here? What's this 260 value, and what's going on? Well, thankfully, other people have looked at KELT-9b too. So Yann and Henning published a while ago that they also got a KP value of around 260 for the hydrogen lines, and they attributed this to being in the extended atmosphere of the exoplanet. And so basically they calculate that the hydrogen should be almost out to the Roche lobe of the planet, and that explains why there is a difference in the KP values. I have some ideas about why this is the case, but I'm still kind of thinking about it, and you can ask me in the questions later if you want to. So doing that, if I now take a face-on snapshot of my differential rotation toy model, and I just expand this out to the Roche lobe, and then I just take snippets. So I just remove, basically from the heel radius to the Roche lobe, and I remove some atmosphere. That will create a VSIS offset on either side. Now, I'm not saying that KELT-9b has like basically partially, it's half of a snippet of its atmosphere going, but this actually demonstrates that the outer edges of the atmosphere are sensitive to fluctuations. So if there is a small difference in the abundance on one side of the planet to the other, that can actually cause a VSIS offset on the order of what we're actually seeing. So to conclude then, if I now go to my scatter plots that I've shown, so I can now roughly explain them to roughly look like this. So when you conduct a chemical inventory of an exoplanet and you manage to get a large number of detections, you should expect to actually see that some of these detections will be in the extended atmosphere of the planet, and some of them will be in the atmosphere that we all like to interpret from. So to conclude, cross-correlation techniques, with our cross-correlation techniques and our multiple planets over different spectrographs, we have 40 new detections, and that allows us to do statistics on those detections. And basically, those statistics have enabled us to uncover the geometrical properties of KELT-9b as a planet. And finally, this was a small thing, but don't quote your KP and VSIS values that you get from detections as the planet's KP and VSIS values. So use the star or use another method to obtain these values itself, because each detection that you have is actually has some sort of atmospheric dynamics at play, and so you're actually not measuring those things. So it makes it really difficult when I go through papers and I try and find these methods to actually figure out how you do it. So use another method instead, and actually use these VSIS offsets to measure the atmospheric characteristics of your planet. Okay, I think that's time, so I'll take questions.
Speaker is going to be Andreas Quirrenbach, who's going to be telling us about, what was it, how to make your workhorse work for two horses. It's almost like a tongue twister.
Good morning. So I hope that it will switch to the full screen mode. Why not? Oh, it's coming. Good. So this is about spectrographs. And I will take some examples, mostly from Carmenes, with which I am familiar. But the purpose actually is to draw your attention to some details that you should consider when you are involved in planning for future instruments. So one example is helium 10830 observations with Carmenes, which obviously worked, but in a way they worked by accident, or perhaps one should say by good luck, because when we built the instrument, there was nothing in the requirements that said that it should be possible to observe this specific line. We built the instrument as a radial velocity machine, and I was very adamant about not allowing any other science case to be considered when we built the instrument because it was difficult enough that way. And so the instrument, for instance, has two infrared detectors. By coincidence, the helium line could have been in the gap between the two detectors, and these observations would not have been possible. And there are a number of other ways in which the instrument could have fulfilled its specified purpose, but be useless for this line. So if we look at use cases for Echelle spectrographs, there's high precision radial velocities, and many of the data that we have seen during this week come from instruments that were built originally for radial velocities. Then there's the cross-correlation spectroscopy that we are talking about a lot of the time. There's this single-line spectroscopy where you are interested in individual strong lines such as the hydrogen Balmer and Paschen lines, sodium D, and the helium line, for instance. There's stellar spectroscopy, and then there's other stuff that you can do with these instruments. And in a way, the scientific requirements for radial velocities and for cross-correlation spectroscopy are rather similar. And this is why radial velocity instruments work well for this case. They are more different in the case of single-line spectroscopy, and therefore, if you are using instruments that were optimized for the RV case, you have to be a bit more careful about whether they are suitable for single lines. So how does this spectrograph specification and optimization work? You start with the basic requirements. You specify wavelength, resolution, sampling, how you want to couple to the telescope, and so on. Then you go through detailed design choices. So there's an optical design, mechanical design. You decide which detector you use and all these things. Then there is detailed modeling, typically in the preliminary design phase and final design phase, where you verify that your design fulfills the basic requirements. You do optical analysis, mechanical analysis, and so on. And then in the end, during the phase where you manufacture, assemble, integrate, and verify your instrument, there are still small adjustments. So you put in little shims to move the optical elements by a little bit. You position the detector and so on. And there are decisions affecting the final performance taken in each of these steps. And the earlier you catch that perhaps something is not the way you want it to be, the easier it is to rectify. You cannot change the basic requirements when you are too far in the project. So the message is pay attention to these things early on. So Again, to take one example, it's about ghosts in Echelle spectrographs. There are a whole zoo of different ghosts. There are grating ghosts. No grating is perfect. There are periodic irregularities in the ruling, and these create ghosts. There are so-called recombination ghosts by double reflections in your spectrograph. There is sometimes blue leakage, so you get the second order from the cross disperser overlaid on the first order that you want. And if it's not blocked properly by a filter, you see it. There are also electronic ghosts that come from amplifier crosstalk. So if you look at, say, a raw image, here are some of these ghosts in Carmenes that are encircled here in green. And if you look very carefully, they all are on a completely horizontal line. Yeah, whereas all the other, if you look at the lines in the spectrum, there's a slight slope because they have a different wavelength, so the cross disperser moves them up by different amounts, so each order has a slight slope, but these ghosts are completely horizontal. So that's a way to identify them. They occur at very regular patterns, and they reproduce each line. So these green ghosts belong to this very, very strong line at the left end, but each and every line has these satellites, and they are periodically spaced. So definitely, if you run a cross-correlation of a spectrum that has these, and you cross-correlate with a spectrum that has a peak at that frequency of the grating irregularities, you will get a cross-correlation peak. And if for some reason that coincides with irregular spacing in a molecular spectrum, you would get a cross-correlation peak with that molecule, just from these grating ghosts. Yeah, there are also a zoo of detector artifacts. Cosmic defects are very well known. There are nonlinearities, and nonlinearities means that not only the depth, but also the centroids of lines depend on the exposure level, or the SNR. There's stitching of the detectors and the electronic ghosts that I already mentioned. And there's memory effects, persistence. The detector, the better the memory of the chip, the worse for your scientific application. You want a detector that forgets what it saw earlier, but some detectors don't. And so if the detector remembers in the night what light you put in during the calibration sequence in the afternoon, that will spoil your spectrum. And that's the reason the detector memories are the reason why you may not be allowed to observe your favorite target. You are interested in this bloody, bright 8th magnitude star that's completely saturating the detector, and the observatory won't let you do that because the detector will be unusable for cosmology for 3 days after you blasted it with your star. So you have to think about these effects. And detectors are individuals. Yeah, Carmenes has 2 near-infrared detectors, and they have a completely different character. They come from the same batch, they were ordered simultaneously, they were delivered together, and one of them has a very good memory and the other one forgets. So they are individuals. You cannot count on detectors behaving the same, each one to the other. So here's an example, say, of CCD stitching. CCDs are in the lithographic process. There's a mask that is stepped across the chip, and that mask alignment has some tolerance. So that means that the pixels are not on a regular grid. There are parts of the CCD that are shifted with respect to the others, and you have to take that into account. Here's a long exposure of our array, and there are bright spots. So this blob on the top left corner looks like this. So again, here you see directly that there are parts of the spectrum that are affected by this and that are extremely hard, if not impossible, to reduce. And if that lands, say, on the helium line, you will probably not do helium spectroscopy with that instrument. So good luck in that we had that this is in a corner where these specific lines have no specific significance. Then there are these ghosts. that come from the electronics, electronic crosstalk. So this is an exposure that has actually 5 bright point sources in it, but each one of these sources is seen many times on the detector. Again, this is a regular pattern that can get you into trouble if you, and it's very difficult to correct for that in software because crosstalk by its very nature normally varies with time. So then there are some more say general considerations. The mantra of building RV spectrographs is no moving parts. No moving part in my instrument, and also very high thermal and mechanical stability. And because these are the requirements for RV, the benefit of that is that it's easy to subtract 2 pairs of spectra, so 1 spectrum taken before transit, 1 in transit, or group of spectra before, group of spectra in transit, because of the stability that was designed in for the RV application. They are great for transmission spectroscopy. The downside is there's no way to adapt the spectral format. It was fixed and then kept forever. This is more problematic in the thermal IR because then it's much more difficult to subtract the thermal effects. Good news is, if you're interested in stability, a lot of that can be actually modeled. So here are series of data points spanning a few years. This is a small shift in the radial velocity that was modeled with a ray tracing model that had all these spectrograph elements in it and took as input thermal, the output of some temperature sensors. So the RV difference between 2 fibers here is correlated with thermal gradient across the optical bench. So you can model that, and that is very highly recommended that you build a model of your spectrograph and run this to understand how it is behaving on the millipixel level. Yeah, sky and background subtraction. Many spectrographs provide sky fibers, but in many cases they are not used. So there are typically difficulties in cross-calibration. But in principle, of course, it makes a lot of sense, especially in the near IR where you have bright airglow lines. Also, stray light subtraction. You may be interested if you are observing in a full moon night, for instance, to subtract the lunar spectrum that is spilling into your spectrograph. This is much easier if you have a slit-coupled spectrograph. Of course, the RV instruments are all fiber-coupled for a good reason. So the question is, if you design the instrument, should one leave out the sky fiber completely? Is there really a reason for having that, or at least is your science case, does that need a sky fiber? Sky is more important at thermal IR wavelengths, so there you probably want it. And then the question is, operationally, would you like to, in principle, that's what IR people normally do, is they nod from one fiber to the other. So that has implications for operations. Finally, detector illumination, flat fielding requirements become very stringent if you go to high SNR, and that detector fringing and efficiency, that depends very strongly on wavelength. So you want a uniform detector illumination, but that is normally not easy in a spectrograph. It's much easier in a camera. And so if you have no specific flat fielding system, you rely on a characterization done before the integration, you miss time-dependent effects. And so the design options there are currently not well established. So to conclude, cross-correlation spectroscopy works very well because you are using instruments that are very well engineered for RVs, and the requirements are largely similar. The emphasis is now shifting for the ALT instruments where planet spectroscopy is becoming the primary science case. And remember, signal-to-noise ratio is not the same as photonoise. Photonoise is one contributor to the signal-to-noise ratio, and all the other contributors are instrumental. And as you crank up the requirement on photon noise with a larger telescope, you have to be more careful about all the other instrumental effects. And design choices and trade-offs happen early in the project, so pay attention to detail even in the early project phases. Okay, so you may want to use your velocity machine, but perhaps you're also using a workhorse. So whatever your spectrograph you are intending to use, it pays off to pay attention to what are the design requirements and solutions are relatively early on. Thanks.
For one quick question while we Right, and our next speaker is going to be Connor Cheverall, who is going to be telling us about high-resolution spectroscopy of temperate exoplanets.
Hi, I'm Connor Cheverall. I'm a PhD student at the University of Cambridge working with Niku Madhusudan, and today I'm going to present my research on high-resolution transmission spectroscopy for low-velocity exoplanets. So, as we've heard a lot about this week, over the last few years, high-res spectroscopy has seen huge success in characterizing the atmospheres of hot Jupiter planets. And that's due to the ability to resolve the individual spectral lines and achieve high-confidence chemical detections. Now, my work focuses mainly on the near-infrared, where molecules such as water, NH3, HCN, and CH4 all show strong spectral features. And these molecules have been detected in a variety of planets, some of which are shown here. But to get these detections, we first needed to trend our spectra. That is to remove the telluric contamination that sort of plagues all ground-based observations. Now, in the optical, this can often be done by modeling it out using something like LECFIT, but in the near-infrared, this contamination is often more severe, and so it needs a stronger, more data-driven approach, such as PCA or CISRAM. Now, these algorithms remove common modes in the time variation of a wavelength channel, which means that, in effect, they remove stationary features in our spectra, such as telluric lines and stellar lines. The spectral lines of hot Jupiter, which are significantly Doppler shifted over the observing night, can survive this and therefore be isolated in this way, as shown in this animation here by Lennart. But because of this sort of reliance on the Doppler shift of the planet and the high velocity that requires, high-res spectroscopy has traditionally been limited to sort of short-period, faster-moving planets. But over the next few years, we're looking to characterize smaller and cooler planets. In this plot here from the Andes white paper, and as presented in a talk yesterday, Andes is going to be able to characterize a large sample of transiting sub-Neptune planets. In the plot on the y-axis, we have the transit spectrum metric, and on the x-axis, the period. And all those planets shown above the red line are going to be able to characterize to more than 5 sigma. This grey region on the right-hand side here marks out all those planets with a period of more than 15 days. And they're marked like that because they're going to be difficult to characterize due to their small Doppler shifts, making PCA and CISRAM difficult to do. So why bother trying to look at those from the ground? Why not just use JWST, which has already been shown to work quite well for these kinds of planets? Well, again, as we've heard a lot about this week in talks such from like Peter Smith, high-res observations offer complementary information to what we can achieve from low-res space-based observations. An example here is a plot from SID showing that at high resolutions we can probe above the cloud deck of these cool cloudy planets, whereas in low-res we might just see a flat line. So in our work here, we've done a series of injection and recovery tests to sort of try and probe the limit of how low velocity we can go. To do these, we've used as a template a real data set taken of TOI 732c, which is a temperate sub-Neptune, with a period of around 12 days and an equilibrium temperature of around 300 Kelvin. These observations was 33 spectra in one observing night, taken with IGRINs on Gemini South, which is an 8-meter class telescope, wavelength coverage in the H and K bands, and a resolution of around 45,000. So to add some context into this and compare this sub-Neptune planet with some common hot Jupiters, TOI 732c has a significantly longer period and like sort of similar or smaller values for KP and the transit duration T14. And all that combined means that the radial velocity shift of the spectral lines for this planet are significantly smaller than you'd expect for a hot Jupiter, just 2.6 kilometers per second in this case. That means, again, to borrow from Leonard's animation, the spectral lines might shift as seen on the right-hand side rather than the left. In fact, the number of instrument wavelength channels by which these planet spectral lines shift over an observing night is just 1.4 pixels, which is less than a typical resolution element. So this is a really difficult planet to observe. So what do we find? So shown here are the results without any injection. So free SNR cross-correlation KPV cis maps, as we've seen all week, for 3 molecules that are expected to be prominent in H2-dominated temperate atmospheres. The white crosshairs shown mark the points where we're like, in a minute going to inject our signals. And as you can see, there's not yet any significant signals seen at these points. Now doing our injection, and we see that we can actually recover these signals to different varying signal-to-noises for the different molecules, SNR of 5 for ammonia, SNR of more than 4 for CH4, and more than 2 for H2O. As you can see, the signals are completely unconstrained in KP, which is expected for these planets due to the very small in-transit phase range. So we can get it at 1.4, but that doesn't really answer the question, what is the lower limit? So how low can we go? Well, apparently we can go all the way to 0. So in this test here, I've injected at 0 KP, 0 V Barry, 0 V cis. So the spectral lines of this planet now have 0 relative wavelength shift compared to the tellurics, as shown in this plot here on the left, where the planet signal is marked in green, if you can see that. So why can we do this? Well, we think it's because of the out-of-transit spectra in our data set. So whereas the telluric and stellar lines exist in every single frame of the observations, the planet signal only exists in a subset of the observations. That means if we have enough out-of-transit spectra, we can create enough contrast between the telluric and or stellar line and the planet signal that a planet signal no longer constitutes a principal component of the spectra and therefore can be isolated using PCA without a significant Doppler shift. On the right-hand side here in these plots, we test this by removing the out-of-transit spectra for the same injections as we did before. So for ammonia on the top, we remove the 12 out-of-transit spectra prior to detrending, and we lose our SNR5 signal, despite the in-transit spectra being identical. At the bottom, for methane, we now inject our signal into all 33 spectra. So there's actually more planet signal in this injection than there was previously when we got SNR of over 4. And yet, without those out-of-transit spectra and the contrast they create, we completely lose our detection. So like moving on and thinking, well, how many outer transit spectra do we need to probe these temperate planets? We think that the quality of the trending is driven by two main factors. Firstly, the number of instrument pixels by which the planet lines are Doppler shifted during the transit, which is called MPX, and secondly, by the ratio of out-of-transit to in-transit spectra. And we explore this parameter space doing like loads more injection and recovery tests, and we show our results here on the left-hand side. In black are shown contours of constant signal to noise, and in white we show the MPX of TOI 732C. And as you can see, even at low values of MPX for these like low velocity, long period planets, with sufficient out-of-transit spectra, we can start to probe their atmospheres and get detections. Like taking a cross-section through TOI 732C and plotting the signal to noise on the right-hand side here, you can see that the SNR increases from like near 0 to more than 3 as we increase our out-of-transit to in-transit ratio from 0 to 1. So it looks like we can like find these signals in the right, under the right observing conditions. I just want to sort of finish up by talking about some of the robustness of these signals and how they vary. So, as I mentioned before, these signals are completely unconstrained in KP due to the small in-transit phase range, and that might be quite worrying. Like, how can we tell the difference between a real planet signal and a signal from, that's spurious, from uncorrected tellurics or stellar activity that just so happens to be at the right V-cis? Well, one thing I tried was to measure the transit duration of the signal on the basis that a planet signal should be constrained in time, whereas the others, probably shouldn't be. And it seemed to work. We managed to get peaks for ammonia and CH4 at the correct transit duration of the planet. A big caveat to this is from the RM effect, which means for molecules such as water, which might exist in the M-dwarf star, signals could mimic this sort of constrained in time behavior. So now looking at how these sort of low velocity signals, after they've been recovered, vary with each PCA iteration applied. And to monitor this, we used a delta CCF metric, which is a measure of the difference between a CCF with and without a signal injection. So we show our results here on the right-hand side with a temperate planet on the top and a hot Jupiter-like planet on the bottom. And I think a few things sort of stand out. For the temperate planet on the top, you can see that after a few iterations of PCA have been applied, most of the remaining planet signal exists at the transit edges. Like, maybe this makes sense. Sort of the transit edges are sort of the high frequency, high variation parts of a planet signal, and so maybe they are the most likely to survive PCA. But what is true is that if you calculate the signal to noise from the edge 6 spectra, so 3 on each side of the in-transit, then you can get an SNR of above 3 for our injections. Where if you do the same for the central 15, which is obviously more spectra, we don't find a signal at all. The other thing that stands out in this plot, I think, are the sort of strong anti-correlated out-of-transit artifacts, which for the temperate planet are actually in trail. So I think both of these suggest that model reprocessing is particularly important if we're going to do low-velocity planets. Not that it's not important if we do hot Jupiters. And that's probably for two main reasons. The first, to account for this phase dependence in the remaining signal after PCA, which is particularly important if you want to do stuff like phase resolve spectroscopy and start drawing conclusions about different regions of the terminator or the 3D structure of the atmosphere. And secondly, to make sure that we capture all this signal. We can't really afford to waste any signal for these cool small planets. So we do this model reprocessing, which I should say, I think it's been spoken about this week, but it's sort of the idea of reproducing the effects of PCA onto the data, onto your model spectrum to ensure a like-for-like comparison. And we do this for an injection of water. And we then compare our trended residuals with the reprocessed model, and we show our results here on the right-hand side, where we get good constraints on VSIS and alpha, which is an atmospheric scaling factor. And then we calculate Bayesian evidence and do a Bayesian detection significance with respect to a null model, which in this case is a like 0 planet. And we find a detection significance of 2.9 sigma for our injection tests, which is more robust and more sensitive than we found before for the cross-correlation framework. So again, it seems that we've managed to recover an injection of a molecule into a temperate exoplanet. So yeah, I'll leave you with my summary slide. Thank you very much.
Speaker in this session is going to be Yann Carteret. I hope I right. And he's going to be telling us about the Rossiter-McLaughlin effect at lower resolutions.
Hello, everyone. My name is Yann Carteret. I'm a second-year PhD student at the University of Geneva, and I'm supervised by Vincent Bourrier. And so you might all wonder why I'm talking to you about the Rossiter-McLaughlin, and especially at low resolution, while we are at the high-resolution spectroscopy. And I'm not sure why I got this talk, actually. But to make things a bit more interesting, I've hidden a lot of two HoRSEs logos in my slides. And the first one at the break later that can tell me the exact number will win a small prize. So first, a small reminder about the Rossiter-McLaughlin effect at high resolution. So if you have a planet that is transiting your star is not across, is not homogeneous across the transit course, and one side is moving towards you, one side is moving away from you, and that distorts the line. So you see in that animation that, let's go back. See that the absorption is evolving in time and can mimic sometime an absorption feature or even an emission feature of the planet, but that's come from only the non-homogeneity of the star. at least what is occulted by the planet in front of the star. So I will explain to you a bit my methodology. So first, we generated a bunch of stellar spectrum with the code turbo spectrum for different stellar types, and that helped us to have 2D stellar grids. So we could have an accurate evaluation of the local stellar spectra across the stellar surface. And a small note on the M star is that the models are often not accurate. So we also combine with observations to have a more realistic spectrum. Then we simulated transits at high resolution with the Eve code. So what this code does is basically do a transit for you with all the absorption. So as you can see, there is a 2D stellar grid, so with local spectra in each cell of that grid, that is then occulted by the opaque body of the planet. And you can also add an atmosphere on top of it, and it solves the radiative transfer. But here in my study, I wanted to isolate the RM effect, so I did not include any atmosphere, only the opaque body, and that's it. So this is a typical spectrum that can be modeled during the transit. So this is at mid-transit at very high resolution. And then I degraded the flux time series to low resolution. And I insist on the fact that I degraded the time flux series and not directly the absorption, because this is really important. Then from this degraded flux time series and also the stellar master out, we computed the transmission spectrum, so this time the absorption is down. And I introduced to you what we call the bias induced by the Rossiter-McLaughlin, which is the transmission spectrum of our simulation minus the transmission spectrum of that same simulation, but without the stellar rotation. So to really get a metric of isolated the effect. So this is the first result that I show you is about very, very low resolution. So what we see is that during the transit, there is a time evolution of the bias induced by the Rossiter-McLaughlin, and there is actually an effect. But what I'm lying a bit there, that if I add then the scale, you see that it is very low and probably well within the error bars of the instrument, and there is no way for us now to detect it or even to get biased by it. Just for a sanity check, I tried to generate an atmosphere and fill it, including that contribution, and I always recover the main parameter, the input parameter of that atmosphere. So at least very low resolution is safe. Just to illustrate you also that we checked for different geometry, and the only thing that it changes is mainly when this bias goes to 0 and changes signs and flips signs. And also you can notice that there are some wavelength dependency features, and I do not have time to explain where they come from, but come talk to me if you're interested. So the take-home message there is that there is no way we can detect it. Then we wanted to go to slightly higher resolution, to what we call intermediate resolution, medium resolution, and we needed a test case for that, which is the very famous HD209 sodium. So earlier this week, you heard the talk of Gloria Canocci presenting you her results about the high resolution HD209 sodium detection, and that were completely explained by the Rossiter plus CLV effects. But because I'm a very picky person, I was wondering if the very famous Charbonneau 2002 detection could also be explained by this Rossiter-McLaughlin effect or not. So what I did is took my simulations from the previous slides. So here you can see the input spectrum, the degraded spectrum. And then I completed at high resolution the absorption feature that were more or less matching what was seen by Casasayas-Barris and the Espresso data. Not perfectly, because there is no CLV effect, and also my whole study is about order of magnitude evaluation and not very precise, in-depth feeding of the signature, but it was quite consistent with the Espresso data. Then we reduced the signal. So once again, I took the flux time series and computed the transmission spectrum and degraded it to STIS resolution. And this is what you get. And you see that you are already the order of magnitude lower in the bias induced by the roster. And I will not bother you with the exact formula, but in the Charbonneau paper, they computed this delta N sodium, which is actually a normalization with the broad wings of the two sodium doublets. And what we obtained is that we could not, by order of magnitude, with only the Rossiter-McLaughlin effect, explain or reproduce their results. So the conclusion there is that the RM alone cannot explain that signature, but we're not claiming that there is an atmosphere, but it supports the idea that at low resolution, you might be sensitive to the wings of the doublet and not necessarily in the core. So if the sodium is only present in the wings and is destroyed in the upper atmosphere, it will not appear in the core, so espresso cannot see it, but maybe lower resolution can see it. There's also a couple of other contributions, so maybe CLV can play a role, but at high resolution, this is a second order effect, so might be also the case for low resolution. Then I'm changing completely the subject, sorry, because my main focus is atmospheric escape. So I also studied how hard is the bias induced by the Rossiter-McLaughlin effect on atmospheric escape, and especially with this instrument of the JWST. And you see that it's not strong unless you go to some exotic orbital configurations, where you get something that is of the order of 100 ppm, which is a bit higher than the error bars on this transit that I simulated. So maybe we could see it, maybe it could influence what you get. And so to go a bit further, this is still a work in progress. I tried to generate a signature at very high resolution, then degrade it, and then generate some synthetic observations based on my simulation that I try to then fit with a code that generates only an absorption signature that I then degrade also to low resolution. And what you see is the density probability of finding the two parameters, the very common parameters, which is temperature and mass loss. And the stars here are the input parameter of my simulation. So what is important here is that in almost all the cases, we never retrieve the input parameters. So there is definitely a bias in the way we fit the transmission spectrum from high resolution to low resolution. So, but if you see here, I computed with a velocity of 0 and a velocity of 10 kilometers per second. They are more or less the same. There are slight differences, but it's not really, really important. And so the RM effect there probably plays a second order effect compared to the way we degrade the signal to lower resolution. So now I'll leave you with my concluding slide and my take-home messages. And just also to mention that almost everything that I presented to you is part of a publication at the beginning of this year. So if you're interested, either come talk to me or directly go to that publication. Thank you.
Any questions or
first speaker is Doriann Blain. He was my postdoc, I don't know how to pronounce his last name. I always say Blain. Talking about a formally motivated retrieval framework. I'll give you a 3-minute warning.
So hi everyone, so I'm Doriann Blain from the Max Planck Institute for Astronomy, and today I wanted to talk about high resolution retrieval framework that we developed and its application to the transmission spectrum of the planet HD 189. And also I will discuss some results about another planet, HD 219. So first I would like to talk about why we put so much effort in developing this high-resolution retrieval framework. And so we'll start with some very basic stuff. So this is the goal of every retrieval algorithm is to try to maximize this local likelihood function that I put behind me. And in order to do so, you have to try to minimize the difference between your data and your model. And to do so, you adjust the parameters of your model. And if you are in the low resolution regime using space-based observations, it's pretty straightforward. Oops, you have your spectrum, your nice spectrum in your data, you have your nice spectrum in your forward model, and you just adjust them together. In high resolution, this is a bit more difficult because we resolve the lines individually. We have to take into account several additional stuff, but more importantly, we have to take into account for the telluric and stellar lines, and also from deformations coming from the instrument. In order to get rid of this nasty three last things, we use something that I will call a preparing pipeline, but in other works it can be called detrending pipeline or pre-processing pipeline. And once you are doing this, you effectively remove the telluric lines, stellar lines, instrumental deformation, but at the cost of deforming the spectrum, as you can see in the figure on the right. So this is for the data. Now for the forward model, so I won't go into the detail, but this is how we model all of the operation that we do for the forward model. But the most important thing is that at the end, we end up with a forward model that looks like the last row on the figure on the right behind me. And then the question that comes to mind immediately is, how do you compare these two things? So you have your prepared data and your forward model. If you look at them, they look very different. So how do you modify your log likelihood function to take this into account? And if you look at the literature, the answer is not extremely clear. So here I will show you two examples. This one is from Brugge et al. 2019. So you can see the how the equation looks like. You have the formal model in it. Here is another example from Petier et al. 2019. You can see that the equation is slightly different. And so there is no consensus in the literature. And so which one of these equations should you use? Well, I don't know, because at best, this equation are justified using an empirical demonstration, but an empirical demonstration doesn't tell you with the limitation of these equations, or if you can use it in your specific case or not. So let's see if we can do a more robust, if you can find a more robust equation. So this is the solution that we developed. So it's one solution. It's not the solution, and it also needs some conditions and some assumptions to be respected. So the first condition is that your data should be written this way. So you have like an exact model with two parameters, element-wise multiplied by a deformation matrix, if it's just the telluric lines and the stellar lines and the instrumental deformation. The second condition is the most important one. So it means that your preparing pipeline must be written this way. So for example, if you prepare your data, it must be your data element-wise multiplied with the preparing matrix. So what your preparing pipeline does to your data. And this I insist that it must be only an element-wise multiplication. So this works, for example, if you do some polynomial fits and you divide the fits to your data. But this doesn't work with, for example, system, because in system at some point you need to subtract something. Then there's some assumptions. So the first assumption is that your preparing matrix could be written in this way. So you have some part that removes the deformation matrix and also deforms a bit the spectrum, and you have some complicated residuals coming from the model or the spectrum, the deformation matrix and the noise. The second assumption is that the deformation part is much greater than the residual, so it means that your preparing pipeline is not dependent on the noise or on the deformation matrix, basically. And the last assumption is that you, basically at the end of the retrieval, your the parameters of your forward model are close to the two parameters. And if all of these points are respected, you end up with this local equation here. So you just have your prepared data and you prepare your forward model in the same way, and that's it. So we can check if this looks correct. So this is a visual comparison. So you have your prepared forward model on the top and the prepared simulated noiseless data on the bottom, and you can see that it's very similar. And you can also check that it works using retrieval on noiseless simulated data. So you have the two parameters in red, it's a red vertical line, and you have the posteriors, and you can see that in this case the posteriors are well centered around the true value, so it means that this framework has no bias. So now let's talk about the application of this framework on one planet HD 189. This is an interesting planet because it has been studied a lot, and even if it has been studied a lot, there is some literature inconsistency inside the literature. So for example, here I show the water volume mixing ratio from different studies. You can see the very recent JWST result as green here. And you can see that there is a lot of spread in the value that is given. Now here is the results for the rest velocity. And you can see that there is also this spread. And in addition, we can see that this doesn't seem to depend, for example, on the species that is studied to retrieve this value. So here are the results using polynomial fittings, like I said, something that works with our framework. So on the left, you can see that we added some of some point, and you can see that it's consistent with the JWST result. Also, so there is a lot to discuss on this retrieval, but what you can see is that it's more or less consistent with a metallicity of 3 times solar and a CTO ratio of 0.1. Most importantly, in this retrieval, we retrieved the mid-transit time of the transits, and this is a very interesting parameter to retrieve, because if you, it's a very good sanity check. In transmission, the mid-transit time is not degenerated with the rest velocity, and so if you are not, if your data timestamps are not accurate, you can end up with an error on your rest velocity of approximately, it can reach the order of the kilometers per second. So it's very important things to check. Here is a results that we obtained using SysFrame. So earlier I said that the framework didn't work on SysFrame, and you can see here why. So you obtain water abundance, which is 2 orders of magnitude lower than with the polynomial fit approach. You also see that the mid-transit time is completely biased. So it clearly means that you cannot use any retrieving, preparing pipeline with every framework. So you have to be very careful about this. So let's now talk very quickly about HD29. Again, this is a planet that has a lot of inconsistencies in the literature. So here you can see results, very famous result from Jacob et al. 2021, and also a very recent result from JWST. And you can see that in high resolution, a lot of species has been detected, and in JWST, not so much species. So again, we made an independent study, so there is no retrieval here, only cross-correlation analysis. And here are the results that you obtained. So you can see that we only detected water, and we cannot, with CCF analysis, you cannot estimate the abundance of the species directly, but what you can do is compare these results to simulated data and see what you can obtain. And here is the results with simulated data with 3 times solar metallicity and CO2 ratio of 0.1. You can see that it fits observation pretty well. And this is the same results using a CTO ratio of 0.8. And you can see that we detect much more species, but that doesn't look like the observation that we have. So I will let you with my conclusion here. So all of these results have been obtained with Petit Raton 3. So yep. You can take a look at this software if you are interested into it. Thank you.
Linn Boldt-Christmas, talking about, I can't see that here, the Exoplanet Exposure Triangle. I'll give you a 2-minute warning.
Sorry?
I'll give you a 2-minute warning.
That's great. Howdy, horse girls. I apologize if I end up clearing my throat a little bit. You see, I'm a little hoarse. No, it's okay. I think it's let's see. Okay. Sorry? I know, I might move around. Can you hear me okay? If I'm here and like multitasking, you can hear me okay? Okay, great. Hello, everyone. Thank you so much for having me here today. So my name is Linn Boldt-Christmas, and I am a final year PhD student at the University of Uppsala in Sweden. And today I'm going to ask and answer the question of how we can get the best possible transit observations of exoplanetary atmospheres simply by adjusting how long our exposures are. Now, modelers and theorists, please don't go to sleep yet. I will start by explaining why this is interesting. And then to the observers, I will end by giving a kind of recommendation on how to achieve this with this technique that I've sort of nicknamed the Exoplanet Exposure Triangle. So to start off on a good note, I'll start off by offending all the stellar people, sorry, by saying that in transmission spectroscopy, we of course have two sources of contamination, one being the stellar features from the host star, and the second being the telluric features from Earth's atmosphere. And as a side note, because I nearly always talk about the stellar and telluric features in the same breath, I've invented the phrase stellurics. I think this is a good piece of terminology, just floating it out there for sort of community feedback, because really it's the stelluric removal that we're trying to do here. And the stelluric removal can be accomplished because we can capitalize on the fact that the planet is, of course, moving, at least more so than the stelluric components. The exoplanet will be blue shifted towards the beginning of its transit, and it will be red shifted towards the end of that event. This means it will have a relatively high radial velocity shift, certainly compared to the small and the no radial velocity shifts seen on the stellar and telluric components. Which is great, because it means that we can tell the planetary lines from the stelluric lines by capturing this radial velocity shift across the transit event by taking a time series of observations, right? And this time series of observations, we're basically just taking a bunch of exposures, boom, 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 across the transit event, kind of like a stop-motion movie. And when we're doing that, we can see from exposure to exposure how those lines are moving. And the number of exposures we take will then depend on how long the exposures are. We can either take a large number of short exposures, or we can take a smaller number of longer exposures. And the difference between exposure length and exposure number, this is what's called the time resolution. And the time resolution, or the exposure cadence, is something that you, as the observer, choose. This is something that you pick out when you're planning your observations. And making this choice is actually not that straightforward, because there are pros and cons to both of these strategies. To take the two extremes as an example, now our instruments are, of course, amazing. We love them, but they're not actually magic, right? The time between the exposure is not instantaneous. So there's a little bit of thinking time that happens between each exposure, and that's called the overhead. Now, what happens if you have a lot of exposures? Well, you're going to have a lot of overheads. And what do you think happens during the overheads? Well, you're not capturing photons from your transit event, is what's happening. So you're going to end up with a smaller amount of light collection if you're spending a lot of time on overheads, which is bad because then you're reducing your signal-to-noise ratio. So obviously we should just take the longest exposures possible all of the time. Easiest talk ever. Well, on the flip side, what's happening during that single exposure? The planet is moving, as we established, but that means that if your exposure is longer, the movement of the planet on that single exposure will be greater than the shorter exposure. And if you have a large movement of your planet during that exposure, you're going to get this smearing effect, where you're recording your planetary lines across multiple pixels, and you're effectively going to decrease the spectral resolution. And the high spectral resolution is the whole reason we're using these ground-based instruments in the first place. So obviously, that's also not good. Oh dear, what a pickle. Obviously, we're in this position where we have different problems arising regardless of which time resolution we're using. So surely there should be some kind of compromise, some kind of Goldilocks zone where your time resolution is not that smeary, but the signal is still pretty good. We thought that sounded like a reasonable ask, so we investigated this, and the answer is yes, with a lot of asterisks. And since we're not all observers, I'm not going to go through all of these asterisks. If you want to know the full answer with all the ifs and buts and whens and hows and gory details, there is a paper published on this work. There will be a QR link added at the end, and of course you can chat to me. But because we're a mixed crowd here, I'm just going to now go through like the holistic, philosophical kind of qualitative answer to this. And so to first very briefly say what we did to investigate this, plan A was time travel, to just do the transit and then go back in time and repeat it with a different time resolution. Didn't get funding for that, so we had to settle for simulations. And we chose an instrument. We work with Cryos Plus, so we modeled Cryos Plus at VLT. And then we chose a exoplanet target. It's not a randomly chosen planet, but it's just like a representative kind of reference case for this. And so we simulated that, but also some alternative timelines for this. We also said, what if you only have half the signal strength? Maybe your target is fainter, maybe you're clouded out half the night. And then we said, okay, well, what if the transit duration was shorter? What if you have less time to capture your photons? Or indeed, what if your spectral resolution was lower? What if instead of 100,000, you only had 50,000? So we took all these four cases, and we simulated them at 9 different time resolutions. Not 9 transits, but the same transit 9 times over, like Groundhog Day, okay? And then to avoid small number statistics, we simulated each of those 100 times so that we had time for sort of trends to emerge. So really, we ended up with 3,600 nights of observations, like 10 years of Cryos Plus time. That proposal was not going to go through. And now that we had this large amount of fake data, we said, okay, let's treat it as we would normal observations. We removed the stellarics according to this SysFrem, this PCA-type algorithm that we've heard a lot about. And then we said, well, we know that this is a simulated planet, so we know for sure what's in its atmosphere, because we put it there. Why not do cross-correlation with the template of that atmosphere? Because then we know we should definitely get some kind of detection, right? Because then we can use that detection strength as our measure of goodness of our time resolution. What makes a time resolution good? Well, it's the one that gets the most robust cross-correlation detection. Now, with 3,600 nights across 10 SysFrem iterations, that's like 3,600 KPV sys maps or values. I'm not going to plot them here, but just to illustrate how the next piece of visualization comes, if you basically imagine that we had all of these different KPV sys things, all for these different combinations of cases, time resolutions, and SysFrem, we took all of those, averaged by 100, and we put them on these kind of heat maps to see how these effects kind of come out. So here you've got the 4 different cases. You've got the shorter up to the longer exposures, and then how that varies with SysFrem in this way. And the brightness of these maps is then what indicates a good time resolution choice, because that's where the detection significance is higher, and the darker is then the worse. I could talk about this for hours, so I won't, and just give like a sort of qualitative summary of what this means. Basically, the headline is, unfortunately, it matters. I'm so sorry, you have to care, because clearly these maps are not all just uniform in color. There is variation, and there's a better and worse choice. The way in which what makes a better or worse choice also varies depending on your system and your instrument parameters, because these 4 cases are not the same, right? The correct choice for one of these cases is not necessarily the correct choice for another. And the way in which this varies is also multifaceted, in that there's no one silver bullet like, okay, always go shorter or always go longer. It depends. You have to take the whole context into consideration. And bearing in mind, this is for 100 nights. Each of these squares is 100 nights, right, averaged. But in real life, we usually have 1. And something that you can see in the paper is that when we looked at these individual realizations, there was a large amount of variations between these 100 of them. Random effects, Sysrom being chaotic. We can talk about that later. And I hope that you all also had time to check out Adam Rains's poster this week. If you don't like Sysrom, that is an exciting new alternative method that he's working on. But anyway, this is a lot of information, and I promised some kind of recommendation, didn't I? So what does this all leave us where? And I'd also promised to talk about this exposure triangle. Now, the exposure triangle, a lot of you may have heard of, this is a real thing. I didn't make this up. This is a real technique used in real photography, like Earth photography. And it's basically just a way to figure out how to best take a photo. Like if you bought a new camera and you were like, hey Lynn, what settings should I use on my new camera? I would be like, I don't know. What are you taking a picture of? Is it a candle in the dark or is it a fast-moving car? And the exposure triangle is just a way to understand if I have some kind of restraint, if I have some kind of parameter that I'm limited in, what is something else I can do to make up for that? And so, for example, if you're taking your fast car photograph, then you're going to be limited by its movement. Okay, so you have to have a quick shutter speed to not make it blurry. That means you're going to get less light. So what do? You can increase your aperture, for example. You can't control one thing, but you can control another, so you adjust accordingly. And the exoplanet exposure triangle, it's just the same thing. So if you've been asleep, please wake up and just remember this one thing. If you remember one thing from this talk, it's the fact that in our exoplanet transit observations, we have to think about the whole context. You will always be limited in some dimension. Maybe you have a short transit, maybe you have a weird science case. There's always something that you can do to make up for that in some other way, because you have to think about the whole picture. And if that sounds a little bit hand-wavy to you, as my final slide, if you're like, I don't care about philosophy, I'm writing a proposal, the deadline's in 45 minutes, what do I do? Please, I got you. So this is the sort of flowchart on how you can think about how to make this decision. First, consider how bad is your smearing really? How bad is your concern? What affects how impactful the smearing will be things like if you have a low or high spectral resolution, or if you have a particularly short or long transit duration. Because if you have a very long transit at a very low spectral resolution, then the smearing is not going to be that impactful or noticeable. So at that point, you might as well go for the longer exposure and pick up more signal. But if the inverse is true, if you got a very short transit duration with a high spectral resolution, that smearing is going to be very noticeable. And at that point, you should probably play it safe and go for that shorter exposure. If somewhere in the middle is true, or if the two are kind of balancing each other in some way, then instead you can consider your signal. Because if you have a very nice, bright target, where you know you can easily get a signal-to-noise ratio per exposure of like over 50, then why not luxuriously save on your resolution and go for that shorter exposure? Whereas if your target's very faint, and you're going to need every photon that you can get, then you should probably go for that longer exposure, even if you're then risking your smearing. And all of these thoughts can be summarized in a sort of handy flowchart that you can at least, I mean, this is the thing, the paper goes a lot about all the ifs and buts and whys, but just to sort of first order, you can follow this kind of logic. Or at least you can claim to be following this logic if you want to use this as a reference and to make it sound like you know what you're doing. And this flowchart can be found in the paper, to which there is a QR link here. It's easy to find because, amazingly, there's no other Boldt-Christmas person on ADS. And with that, I thank you and leave you with my conclusions and take any questions.
Bibiana Prinoth talking about cross-correlation challenges in the Andes era. Sounds like fun.
So I need to make a check. I'll take that one. I'll have to do a quick check. I'm sorry. Give me a second. If I do that somehow. Let me see. We'll see if that with the sound is going to work. This is going to slide down. I'm sorry. Wonderful. Thank you so much for having me. My name is Bibi. I'm a PhD student at the university in my final year, and I'm going to talk a bit about challenges for cross-correlations, in particular also focusing a bit on Andes. I would like to take you on a small little thought experiment. Imagine you're studying horse life on Earth, but all you look at are unicorns because they're bright, they're easy to spot, have a lot of colors. What else would you want to study? You would like to study Andalusian horses, or you would want to study Mustangs, or maybe even Shetland ponies. Yeah, I'm not a horses person, I just Googled those and they were the first ones that came up. But if you haven't realized by now, I'm talking unicorns as ultra-hot Jupiters, and in my case, the horses that I would like to look at are warm Jupiters. That brings me to the warm Jupiter opportunity. I plot here this very famous diagram by now, or plot of the equilibrium temperature against the planetary radius. And I put here a little box for our unicorns out there. And as Mike Lyon nicely said during his presentation, they just keep on giving, so don't stop looking at them. I'm not going to say that. But there are also some other horses here that we would like to look at, and they have some special features or characteristics that are very nice about them. So for example, we can look at formation locations, or even formation pathways, or migration pathways, depending on eccentricities. And also their atmospheres are sort of unaffected largely from the stellar radiation because they're just not so close to their host stars. Also, hot Jupiter systems, or ultra Jupiter systems, are often circularized, which is not the case for these warm Jupiters, and this is going to become quite important in a minute or two. I want to talk about caveats. Some of you might know that I work with Yann as my supervisor. My academic grandfather is Ignas Snellen, and I want to talk about caveats in the cross-correlation technique. Sorry, academic grandfather. If you observe from the ground, you have tellurics. Linn already nicely introduced that before, so I don't have to spend much time on it. But you also, in my case, I look at transmission. You have a star and a planet, and you have the RM also going between the two. So you have essentially 4 components in your spectrum. And we often say, oh yeah, the star is constant, let's just divide it out. That's not true. So the star is in there. I will call it stellar contamination as Linn did, or stellurics as Linn did, if I want to combine the two. We also have a planetary spectrum, which is what we want to get out in the end. And then we have this interaction of the RM that is also very important, of course. Let me give you an example. Here we have this planet called K2139b. It's a warm Jupiter, you don't really need to know all the details. But what I'm showing you here are the radial velocity extent of the different features. In blue you have the planet, in orange you have the star, in dotted dark orange you have the tellurics, and in dashed green you have the Rossiter-McLaughlin effect. You see one thing very clearly. The star, the planet, and the Rossiter-McLaughlin effect are pretty close to each other, right? And for the tellurics, we were kind of lucky looking at this observation because they just ended up being sort of offset due to the systemic velocity, but also due to the barycenter velocity of the Earth. So this one was actually quite good. So maybe that also as a hint for you observers when you look at your transit windows, maybe quickly check what the birth is going to be and if the sort of tellurics are going to move away from your rest frame. That might actually help you a little bit. Here's another example where we have the star, tellurics, and the RM that are close in radial velocity space, and the planet then occupies a different regime. And I give you a little spoiler here, this planet is on an eccentric orbit. So what do we learn? This system architecture matters a lot. I want to take this system architecture as a proxy. So I initially made this kind of roadmap, flowchart, whatever, and then was like, okay, let's put some HoRSEs there because that's a theme, right? But then I got sort of, I got inspired by people like Peter and also Fabio showing nice animations. So I spent all my free time this week actually putting this in an animation. So first what I'm doing is, the observer is from the bottom of the slide, and you will only have omega, which is the argument of periastron, facing towards you. And the only thing I'm doing here is I'm changing the eccentricity of this orbit. This is for this TOI 3362b, it doesn't really matter too much, just as an example. And on the right side, you see one thing very clearly, also linking back to Linn's talk, so perfect that she had to talk before me. You see the sort of decrease in the transit time, or transit duration. So therefore, it's actually kind of important how you're going to observe this. You also see one thing, that this is for an aligned orbit and a v sin I of 24 kilometers per second. You see the planet and the RM are going to overlap at some point, or the planet goes through zero and we're not moving very fast anymore. So this is really challenging to actually get your planetary signal out. Now, let me choose an eccentricity of 0.7 and just vary omega, so turn this orbit around. Again, we're observing from the bottom of the slide. And you see, here it's going to break for a second, just close your eyes, but I didn't have time to fix that one. But you see, depending on how the orbit is aligned, you will have the planetary velocity away from your system or from your star. I didn't plot the tellurics here because I didn't have time to add that part. But I would say that it's actually quite an important part, and if we put this together, in particular for non-eccentric orbits, of course, we can see that we have these 4 components that are going to lead us to figure out what the velocities are, or define what these velocities are. I'm not saying you can go fly out and change the orbital configuration of your system, but you can at least pick out what you're going to observe based on that. And you may want to invest some time in figuring out what the alignments and the v sin i's are of your system in order to figure out where the RM is going to cross and stuff like that. So you have the eccentricity, the projected orbital obliquity, the argument of periastron, and also the v sin I. On the very left side, you see zero eccentricity, so there's not much you can do. Omega is defined as 90, so that's just how it is. There, it's going to be very, very hard to actually disentangle your signal. While if you go to higher eccentricities, you have those different cases here for 60 and 240 degrees, and you see immediately for 60, where the argument of periastron is facing towards us, you move relatively faster, so that's why it's brighter on the orbit, just because this is how you move on an ellipse. And for example, on the 240-degree case, you would want to observe maybe an emission or something like that, because it's going to move relatively fast there. On the right side, you see a plot argument of periastron against transit duration, and you see immediately that this changes quite drastically if you increase the eccentricity. So you end up gaining a lot here, but also losing a lot here during your transit. So think of those orbital configuration and some smart observation planning for your tellurics. We did that with a sample of 6 warm Jupiters that were observed with espresso in order to actually figure out their alignment. So it was a study for formation pathways more than it was actually to look at the atmospheres, but our collaborators gave us that data. And as you can see, we have 6 targets. 4 of those are circular and 2 are on eccentric orbits, and they will become important. I think the thing that you would like to note is that these planets are not inflated, so I had to do some assumptions there, some modeling. I will get to that in a second. I will cut to the chase, and this is not something new. We're not seeing any water with espresso. You also see we're quite bad at getting some of the telluric features out. I plot here, this dotted line is always where the tellurics are, and you see we have quite a bit of leftover there. This is also because these residuals come from not really optimizing the observations for atmospheres in that sense. So we don't have enough signal to noise in many of them in order to get it out. And yeah, for some of them you see this really nice overlap where you have actually no chance of getting anything out. Another thing that one could maybe mention is, apart from the telluric fact here, this was a telluric correction with molequid. Maybe someone wants to try this with PCA and see what comes out of that. We then had a look at Andes, and I have really good news for you, because on June 5th, I screenshotted that from X, there was the signature from ESO with an international consortium of institutions. You see on the picture, which is a bit small, you see the Director General of ESO shaking hands with the President of ENAF. So this is really happening, guys. I'm looking forward to it. I want to point out a few very important aspects. I'm just going to pull them all up. We have a really superior collecting power given the size of this mirror. I quickly did the back of the envelope, like this division of sizes, and you get a sort of a boost of 20 to 25 in signal to noise due to the massive mirror. Just let that sort of sink in for a moment. We have a similar resolving power with Andes, but what I think is very important is that in comparison to other infrared spectrographs, like for example CRIRIS Plus on the VLT, we will have this continuous wavelength range. So we don't have to choose which band we're going to observe. And hopefully, I don't know how exactly, so maybe I want to talk to Katja about this at some point, we get the K band as well. So maybe there's some carbon monoxide challenges in there as well. We did some predictions for Andes. We used FastChem and we used Petit Latrans. This was still the old version, so I should try the new one as well. And we modeled the two transmission spectra of these eccentric planets. And one thing you see immediately is there's a different scale on the y-axis. So you see one thing for this TOI 3362b, which is also an observational bias. Ask me later if you want. This is a very, very heavy planet. It has a 4 Jupiter mass, and therefore, yeah, it has a high surface gravity, so all these features are not going to be very easy to get. But one thing you see from this plot, for example, is if you go to these longer wavelengths, you're probing deeper and deeper lines. Thank you. You also get a very high signal to noise. I already talked about that for Andes, and you also get access to more of these bands, and also particularly CO. Again, cutting to the chase, these are very optimal predictions. We did not include any tellurics. I did not vary anything with the star. I just assumed constant stellar model. But we have detections for water and also carbon monoxide in this TOI 677b, and you see one could still optimize the telluric position a bit, depending on when one observes. For TOI 3362b, I would say it's kind of a bit hopeless to actually see something there. You can correct me on that if you want to. I want to talk about everyone's favorite, because my supervisor said that you cannot come up as a rock star and don't talk about your biggest hit. These are the predictions for WASP-189b. On the right side, and it's really pun intended because this is a very bright target, you will be able to resolve these kinds of TOI band heads, for example, and also the CO lines if we actually get this K band. One small little tremble. No, actually, a big earthquake happened last night in Chile, and they're currently realigning the instruments. So in case you had observations this night or next night, might not be happening. I'm really sorry. Also, this is little me back in November, standing in front of the ELT with my partner. So this is really happening, guys. It looks pretty different by now. I have some takeaways for you. First of all, the need for speed really constrains the accessible systems for these atmospheric studies with cross-correlation. We've heard that at Connor as well. And here the focus on warm Jupiters and not on sub-Neptunes. But these long circular orbits are going to be hard. And I want to sort of really put this out there. This is challenging, and we as a community need to think about how we're going to do that. Also sort of a shout out to Lorenzo's data challenge here. So if you haven't voted there, please do that. As a last thing, I wanted to show you something from the thing I grew up with the two horses I grew up with. These are Bibi and Tina sitting on Sabrina and Amadeus. I put a translation there for the text. Oh wow, I didn't realize the music is going to continue, but so be it. This is sort of a very fun thing for all the German speakers. For me, it was very obvious that everyone would be like, oh, she's Bibi Blocksberg, but it never happen. And now you all know about it, so you can call me Bibi Blocksberg from now on. Hex, hex. Thank you. I might move that back to the
Our last speaker for the meeting is Emily Omaya Garvin, and she'll tell us what we can do when using machine learning for detecting species, if I understood this correctly. So,
thank you. So, hi everyone. So today I'm going to talk to you about how we can actually find those molecular species using convolutional neural networks on cross-correlated spectra. So, as Paul said, my name is Emily. I'm a student at ETH in Zashakwan's group, and I work mostly with integral field spectroscopy. So basically, Jann's already introduced the cross-correlation method, so I don't have to go into details into this, but in the best of worlds, when things go well, we would expect to observe a very nice cross-correlation peak when the spectrum and the template are actually in agreement, and if this is not the case, we would expect to not observe a peak. As we have seen this week, things are a little bit more complicated than this, and this does not always happen. So I'll come back to this. So molecular mapping is actually a natural extension of cross-correlation spectroscopy. So it's basically if you have an integral field unit, you can just cross-correlate every spatial pixel of your IFU with a, for example, single molecular template, and you can highlight the planet at its RV in the cross-correlation cube. So we actually saw that in some cases, detection can get challenging, and this is a typical case of archival PZLB data. So it's a known brown dwarf, which should be easy to detect. And in the first night, we can see that we have a very strong Watcher signal. And on the second night, where the seeing conditions are lower or worse, and the air mass is not so good, then we have troubles getting such a signal. So the peak is really dampened. And for CO, actually, this gets even worse. So that's a little bit disappointing if you actually spend some time writing your proposal and you get your data and you actually don't really see what you actually expect to see, although especially when you know that it should be possible, right? So I'm interested in those not so well-behaved spectra and cross-correlations, basically. So when the noise is a little bit overwhelming, when it becomes non-Gaussian, when you have systematics from like stellar residuals or tellurics, and what can we actually do? Are there like extra new solutions that we can think of? So I'm not going to go into details of how we assess detection with a signal-to-noise ratio, but several ways have been explored in the literature. I've tested most of them, and honestly, it really does not change the conclusions of my results. I just went with one for this presentation. Let's start with an easy exercise where we simulate a lot of those like donkey cross-correlations, so the ones that don't behave so well, where the signal is quite overwhelmed by the noise. So I simulated 24,000 spectra, with half of them containing Watcher, so basically a planetary atmosphere with Watcher, and the other half has either planets without any Watcher or just pure noise. And we try to score basically all those signal-to-noise, all those cross-correlations with the signal-to-noise ratio to see how many of those spectra we can actually find when the signal is so dampened in the noise. And so we actually see that in this case, the signal-to-noise ratio is really not doing a very good job at separating the two groups. So essentially, we plotted the signal-to-noise ratio scores for the group with Watcher and the group without Watcher. So you can really see that they really overlap, and you have to go very conservative to basically assess the detection without significant contamination in your detection sample. So the idea is that we can actually see or think of signal-to-noise ratio as a classification method. So once we have our scores, we can actually set a threshold to assess if the molecule is there or not. Usually this is done based on assumptions of, again, Gaussian data, and it strongly relies on those like Gaussian uncertainties. What we can do is be a little bit more agnostic to the distribution, for example, and then we can use machine learning algorithms and use probability scores in a similar way to classify our data. So before I go into the details of how the CNN work, I just wanted to highlight something. So we did a little test also with a few simulated spectra, and we cross-correlated them with single molecular templates spanning different temperatures and surface gravity. And we can actually see that whether the template actually matches exactly or not, we always observe either clear symmetric patterns in the cross-correlation or strong molecular harmonics in those for CO, for example. And so those harmonics are persistent even if we have uncertainties about the temperature and the surface gravity of the planet. There's still a strong molecular signature that is underlying. So that's quite interesting, and this is something that we actually leverage for the convolutional neural networks. So now, instead of cross-correlating with our spectrum of our planet with only one template and trying to get the best match, we will actually be a little bit more agnostic and say, okay, well, we know our data maybe from photometry. We know where to point, we know where to observe, but it's our first spectroscopic data. We maybe don't have very good constraints on the temperature or the surface gravity. So let's just be a little bit more agnostic, and we cross-correlate our spectrum with several templates spanning different temperatures and different surface gravities. So then we will get a stack of cross-correlations, so what we call channels, and machine learning jargon. And it's a little bit of the same idea as if you apply convolutional neural networks on images. You basically apply a filter along your image, and the channels will be, for example, RGB images. So you're going to look for common patterns across the red, green, and blue images. And here's the same idea. So we look for the common molecular feature along cross-correlated spectra with different temperatures and surface gravities. So we apply the filter, or in general, like the CNNs. The first layer is a filter. So we apply the filter across those cross-correlations and along the RV to look for this common signal. So that's basically the results on the scoring distribution. So we can see that the CNN does a really nice job in reinterpreting the data and actually separating the two groups. And from there, we can actually assess, so evaluate or use a threshold to evaluate how many planets we can actually detect. So in this case, I don't use the false positive fraction. It makes a little bit more sense to use the false discovery rate. So basically, we constrain the contamination of our detection sample to be maximum 5% false positives. And this is actually what we can get. So just for the record, I don't know if I precise this clearly, but so it's simulated planets in real symphony noise, right? So the signal-to-noise ratio will only find, out of those 12,000 planets with water, it only finds 88 of them. And the CNNs actually can find more than 6,000, so we are more than 50% sensitivity. And, that's went backwards, sorry. So we already discussed the flexibility regarding planet properties, and this also might include the fact of adding secondary molecules or other properties that you're a bit unsure, and you can actually add this variability into your data, which comes in quite handy. And the second nice thing about this method is that we actually only trained it in the RV dimension. So we actually do not use 2D CNNs. It's one-dimensional CNNs, and they only operate pixel per pixel. So that means that technically it's built to be adaptable, ideally to other instruments and not only to IFS. And we also have the advantage that we're actually not learning the PSF, because this could be quite dangerous with machine learning, where it starts to highlight neighboring pixels because it learns that they have a spatial correlation, right? So we are also avoiding this type of drawback. So just to show you that it actually can work to train on individual pixels and then reconstruct your cube. So what we did is we resimulated PZLB and we injected it into its true noise. And this is basically a simulation of the good conditions. Then we injected, again, this signal into the real noise of the bad seeing conditions. And we also drowned a bit the signal into the noise to make the problem a little bit more difficult. Then we applied the signal-to-noise ratio scores. And we applied the CNNs. On top is water, below is CO. And we actually get to recover the signal in with high certainty. So that's actually really nice. Again, it's simulations. Up to now, I didn't have a test on real data yet, but I worked like crazy during this week just to try and get the first results. But those are really preliminary and they are conditional. So it's still open research, and we still have to make much more tests to really assess that it actually works on real data. So do you remember this kind of sad case that we had at the beginning in the introduction? So I constrained the color bar in the introduction just to have the two plots comparable in terms of intensity. So now I just unconstrained discolor bar for the signal-to-noise ratio, so you can still see that there's a little bit of conspicuity. We can still see slightly the planets. And if I apply my CNNs, this is what I get. So it's already a nice first result. I was the most skeptical, I think, about this, so I'm very happy about those first results, but we have to make much more tests to be able to assess the limits and the applicability of the data, on the data. So those are my conclusions. So in general, this method is expected to be useful when your noise presents non-Gaussian features and systematic effects. The reason for this is that actually, normally we know that there is this nice mathematical optimality condition between cross-correlation, which is actually a maximum likelihood solution, but this only works under the Gaussian assumption. And if your noise starts to present systematic effects and non-Gaussian features, then this nice mathematical relationship is broken and the cross-correlation starts to be suboptimal. And this is the only case where we actually managed to do better with the CNNs, right? So we also did some tests with a pure, perfect Gaussian noise, and we would get the same results as the cross-correlation. Yeah, so those are various situations where you could get maybe some non-Gaussian features in your data. The method has been built and is testable now for Iris and Miri, and we have actually some data. We're still working on it, so most of the team went on holiday, so I could not finish this for the presentation, but we're working on the data. We're going to try this in ground-based higher resolutions, and we also had a few discussions with some people from the team of Harmony and Metis who are interested in testing this, and I got a lot of suggestions from the community to test the search for maybe isotopes or trace species. So I'm also very open to discuss this. And yeah, generally it's also built to be transferable and adaptable to slit spectroscopy or transmission spectroscopy, but on this side I have much less knowledge. I would love to have input from the community. So I love mules, so that's my last picture. And I'm actually a statistician, I'm not an astrophysicist, so on day 5 now you finally know it. Yeah, so I'm happy to take questions from now.